I'd now like to invite Professor Vijay A. Singh, Chairperson, Academic Committee, for the academic report of APhO 2022. Thank you.
Good afternoon, and very respected faculty members, vice chancellors and chancellors, and director general, very dear students, and all my respects also to the staff over here, who have done a wonderful job over the last 1 week. So, I have to describe the academic programs, so I shall confine myself to the theory part. My young and dynamic colleague, Praveen Pathak, is somewhere around. He will describe the experimental part. And I will take about 5 minutes of your time. And I realize that the audience may not, that I'm supposed to give a non-technical presentation of the academic tasks. So let me try and do it. This whole exercise began in earnest about 10 months ago in August, when we all assembled in Graphic Era University on the other side and tried to hash out some problems. Then over a period of 10 months, we met at least 5 or 6 times in Graphic Era. And we had very gracious hosts, I mean, uncomplaining and unstinting support from Graphic Era, host of institutions. So that was a large part of the encouragement that we received, and the fact that we could do it was partly because of this. Okay. So let me describe. There were 3 theoretical tasks. The first task, each task takes about 10 points, to just give you an idea. So it's 30 points, and there's 20 points for experiment. The first task was basically, how should I put it? This is the centenary year of our founder of IIT, Dr. Khandelwalji. Okay. And one of his closest associates, Professor R.N. Kapoor, who is 91 years old, is also present among us. So the problem that we made was also a centenary problem. It was called the Stern-Gerlach experiment. It was done exactly 100 years ago by Otto Stern and Gerlach, and it fetched Otto Stern the Nobel Prize. And it is an experiment, so it's paradoxical. The problem is a theoretical problem, but it was the analysis of this setup that Stern-Gerlach had that we presented as the theoretical problem. And what did this problem do? This problem basically led to the discovery that the electron or the proton, which is the fundamental particle, has a charge, of course, it has a mass, and in addition, it also has a magnetic moment. It is a small magnet. It is a tiny, tiny magnet. It's a billion times smaller than the regular magnet that you see in everyday life. But it was this discovery which was seminal and fetched the Nobel Prize. Now you might say, what good was this? Okay. So I'm reminded of something when Faraday was asked, Michael Faraday, the great British physicist, experimentalist, when he discovered electromagnetism, magnetic induction, he was asked, what good is this? A young high society lady asked him, what good is this thing? So he said, man, what good is a newborn baby? That was his response. And then a politician asked him, what good is this, Professor Faraday? And he said something very interesting. He said, I don't know, of what use it is, but I'm sure that one day you're going to tax it. That was his response. And sure enough, this magnetic moment, this tiny, tiny magnet that you have, which the electron and the proton has, is used in every city in the magnetic resonance imaging machines that you see. The MRI machines all across the globe use this fact that the proton has a tiny, a million times smaller magnetic moment than what you see in everyday life. So that was the first problem. And imagine how small the magnet was, and imagine how fine that experiment would have been. So that was the first problem. It was designed by Professor H.S. Money, who was the Dean of Faculty, ex-Dean of Faculty at IIT Kanpur, and then became the founding director of the Harishchandra Research Institute in Prayagraj, and a young member, Dr. Gautam Datta, who is from the Ambani Institute for Information and Communication Technology. So the first is in North India, and Gautam Datta is from West India. The second problem, okay, and to begin the second problem, I'm reminded of a verse, and the foreign audience has to excuse me, I'll translate it for them. I was reminded of a verse by Jaishankar Prasad. It's a very famous epic poem called the Ramayana, and the very first 4 lines describes the mental state of Noah after the great floods. The Indian equivalent of Noah is Manu, and it describes his state. He's sitting on the hillside of a very majestic mountain, and the way it goes, and again you have to excuse me, I'll translate it for you, with the foreign audience. Upar, niche jal tha, upar him tha. Niche jal tha, upar him tha. Ek taral aur ek sagan. Ek tattva ki hi pradhanata, kaho use jadya chitta. That is, there is only one element. There is only one. The water is water, but it takes 3 forms. It takes the form of ice, it takes the form of water, and it then takes the form of water vapor. And that is what the second problem is about. It's about a phase transition. You have a metal, and this metal, for example, is a metal, but if it is at high temperature, it's paramagnetic. If it is at low temperature, it is ferromagnetic. It becomes a magnet, or it does not become an active magnet depending on the temperature. And there's a beautiful theory by the great physicists Landau and Ginsberg called the Landau theory of second order phase transitions. How, I say, how do I explain this theory to a 12th standard student? So we cooked up a mechanical model to explain it to this 12th standard students, and this mechanical model became task number 2. And this model was developed by 2 young faculty members, Professor Shitikant Das, okay, he is from IIT Kharagpur, he's faculty there, and Dr. Parmendra Ranjan Singh, who is in the audience, he's from a college, he's the principal of a college in Bihar, in Narayan College, Goriakot. So this is from East India. This problem is designed by the East Indian crowd, but with absolute help, an unstinting help from the academic team, whom unfortunately I cannot name one by one. The third problem was designed, was basically, let me put it, had the Indian touch. So we had Landau, and then we had something else, Otto and Stern and Gerlach. The third problem had an Indian touch. The Himalayas have fascinated Indians for a long, long time. And I'll quote a verse by Kalidas, a Sanskrit poem 2,500 years ago. Okay. And what he says about the Himalayas is that Tarasya Devatma Himalayo Nam Nagadhiraya. To translate it, he says the northern part of India consists of the Himalayas, these enormous Himalayan mountains, which is loved by the gods. It is the house, it's the place where the gods reside, he says. It is not just, and you'll be surprised to know that it's not just the Indians or even say, our neighbors like from Afghanistan or China who are fascinated by the Himalayas, but even the British were. And the great Scottish physicist Maxwell around 1873 wondered if you could see Mount Everest, the tallest mountain in the world, from the plains of Hindustan. And why couldn't you see it? Because after all, air absorbs. And when air absorbs, it is basically, the light gets dimmer and dimmer, and you may not be able to see, say, from Delhi or from even northern, for example, a place like Patna or something. So he asked this question of another great physicist, Lord Rayleigh, and Lord Rayleigh put it on the back burner. Maxwell died 6 years later in 1879. Lord Rayleigh visited Darjeeling in, I think, 1897, and he remembered what Maxwell had asked him. And he wrote a very famous paper. It's one of the most famous papers in physics in 1899. It is this paper that we brought down to the level of a 12th standard student and asked as task number 3. In addition, we put a social context in this. We said, what if there is pollution? Would Mount Everest be visible? And the answer turned out to be no. So we had a social context in it, and the problem was held by two people, Dr. Amitabh Vermani, who is faculty at the Chennai Mathematical Institute, and Professor A.C. Vianney, who was a retired professor from Central India from government college. Of course, once again, supported by a great team of great academic team of 10, 15, of 20 people. I would basically, these are the three tasks which I had to describe to you in non-technical terms. And I will end by saying that it is not, how should I put it? There is a lot of support that we got from the staff, and an enormous support that we got from the young student graders who were assembled here for the last 10 days. So I wish to thank them. Thank you very much.